In the previous chapters, we've talked about how different forms that matter can take different kind of forms. Like metals, they have the three-dimensional structures with the close-packed metal cations with the free-flowing electrons. Ionic compounds, they have that crystal lattice structure with alternating cations and anions that are held together by the electrostatic forces or the opposites attracting each other. In ionic bonds, our noble gases exist as individual atoms, and in this chapter we're going to look at something called molecular compounds. And so when we form molecular compounds, we do so with something called a covalent bond. So molecular compounds are molecules that are made up of individual molecules. And the molecular formula is going to show the quantity of each atom. So in a diatomic molecule, remember the prefix di means two. So a diatomic molecule has two atoms. And they're exactly the same atom. So an example of a diatomic molecule would be H2 because there's two hydrogen atoms that are bonded together. So in nature, chemical bonding is favored because most atoms will then have a lower potential energy. And so if two atoms are far enough away that they will not interact, their potential energy will be zero. So remember, we have the electron cloud of an atom, and that's that outermost the outermost edges where the possible electrons could be. And so if those electron clouds have a distance between them that they will in no way interact, that's when their potential energy will be zero. So as those atoms get closer, as they move towards one another, those electron clouds are going to start to get closer and closer, and eventually they're going to overlap and begin to interact. So if the electrons from two atoms begin to repel each other, we're going to have an increase in potential energy. If the attractive forces develop between the electrons and the nucleus, the potential energy will begin to decrease. So right about here, the electrons are going to be interacting more so than the electrons and the nuclei. So here we would have an increase in potential energy. But once they get past that, and now these electrons are going to start to interact with the positive nucleus, our potential energy will now begin to decrease. And so this ideal distance of that lower potential energy is when a covalent bond will form. And this is a bond in which two atoms share valence electrons. And they share them in pairs, and it can be one pair or two pairs or three pairs. This is when the potential energy is at its minimum. So we can diagram these covalent bonds with Lewis structures. So we've kind of started practicing with Lewis structures already, and we know that Lewis structures or Lewis dot diagrams or dot structures show the valence electrons. And so a Lewis electron dot structure is the diagram of the structure of molecules that are held together by covalent bonds. So if we were to draw the Lewis structure for two individual hydrogen atoms, we draw the hydrogen atom with one valence electron, and then we have a second hydrogen atom with its valence electron. And so when they bond together, they will bond to form a single covalent bond, and this is when you share one pair of electrons. And so remember, every molecule or every bonding situation strives for that octet or noble gas configuration. And so in the case of hydrogen, it's going to strive for that helium structure. And so helium has 2 valence electrons. And so when these 2 hydrogen atoms bond together, we're going to draw it like this. We're going to simply join together those hydrogen atoms. And this right here is showing a single covalent bond. And we know it's a single covalent bond because each atom is contributing 1 electron to the pair. So we can show this in another way called the structural formula. And this is a formula that shows the arrangement of atoms in a molecule and represents a covalent bond. But instead of using the dots, we use a dash. So this dash right here makes this a structural formula, where this formula, because it has the dots, it's that Lewis electron dot structure. So the octet rule in covalent bonds, it's the same as with ionic bonds. Everything wants to be like a noble gas. So our single covalent bonds, they form when 2 singly occupied orbitals overlapped with each other. So for our hydrogen, we know that each hydrogen, it's 1s1. So here's our 1s1 for the first hydrogen, and here's our 1s1 for the second hydrogen. And so those orbitals are now going to overlap, and it will give the electron configuration of 1s2. Fluorine, same way, has the 2 orbitals here. They're both half occupied, and so those will be the 2 orbitals that will overlap. Lone pairs of electrons are a pair of electrons that are not actually involved with the covalent bond. So for fluorine, when we have 7 valence electrons in its dot diagram, 1, 2, 3, 4, 5, 6, 7, the electrons on this side, and this side, they're already paired up, so they can't be involved in the bonding, and so we call those the lone pairs. Whereas this electron right here is in an unpaired orbital, and so that pair is actually able to bond with a second fluorine atom, because it would have the same situation, that it's only half filled. So here, these 2 electrons can form a single covalent bond. And they do, and we can draw it in that structural formula with just the bar between them. Notice when we use the structural formula, we don't have the lone pairs of electrons drawn in with them. They're just assumed to be there. So let's practice drawing these Lewis dot structures, and we're going to start with water. So actually, before we do that, we should go through some general rules for these. So not that these rules will necessarily pertain to this one, but these rules will help you with your assignment. So first and foremost, carbon will always be the central atom in the drawings. And by always, it's probably almost always. If there are multiple carbons, they will always bond together. And by always, it's almost always. And then the last little hint here is that hydrogens almost never are never in the center of a molecule. They always go around the outside. So when we're drawing the Lewis structure for water, we have H2O. Oh, and last and foremost, total number of valence electrons has to be followed. That's the biggest and most important rule here. So your first step when you do these is to figure out how many valence electrons you have available and need to place in these structures. So oxygen contributes 6 valence electrons, and since there's only one oxygen molecule, we know that there's a total of 6. Hydrogen contributes 1 valence electron, but in water there's 2 hydrogen atoms, so for a total of 2 electrons being contributed by hydrogen. So you add those together and we have a total of 8 valence electrons that are going to be involved in this bonding process, or potentially. So start with anything other than hydrogen. So in this case, our starting atom is going to be oxygen. And go ahead and just draw your Lewis structure or your dot structure for oxygen. So we have 6 valence electrons to place here. So 1, 2, 3, 4, 5, 6. And it doesn't really matter how you do it, as long as there's 6 of them. So then it might help you to color code these so you can visualize it better. Eventually you will get to the point of not needing to. And in Notability, if you do these in Notability, it works really slick because when you draw these separately like I have, you can use the scissor tool and cut and drag them to where you think they should go in the structure. So here we can see that there is an lone electron here, 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 and here. And so another rule is no unbonded electrons. Everything has to be bonded or paired up. So unbonded or paired means the same. They have to be bonded. So what we can do is we can slide this hydrogen. See, this is where your cut tool in Notability will be nice. And pair that there. So now those 2 electrons are paired. And then we can take this hydrogen and pair it with this unbonded electron. And now you can see that we should check that we have 8 valence electrons. So go through and count 1, 2, 3, 4, 5, 6, 7, 8. All 8 of them are there, so we've satisfied that rule. We can see that there are no unbonded pairs. And you can also see that for each element, its octet rule is followed. So you can see that oxygen now has 8 electrons surrounding it. And hydrogen only wants 2 valence electrons, and each hydrogen atom has its 2 valence electrons. So this would be an acceptable Lewis structure for water. Now, could you have placed your hydrogens over here and the 2 unbonded or lone pairs of electrons down there? We should really change this to no unpaired. My bad. Not unbonded. Unbonded is fine as long as they're paired. Unpaired. And so this would also be an acceptable Lewis structure for water. Again, just as long as each atom has its octet or noble gas configuration followed, and you have your total number of valence electrons met. So sometimes some molecules cannot satisfy the octet rule with a single covalent bond. So an example of this would be C2H4. So carbon, there's 2 carbon atoms. Each of those bring 4 valence electrons for a total of 8. Hydrogen, there's 4 hydrogen atoms. Each of those bring 1 valence electron for a total of 4. So we need a total of 12 valence electrons in this structure. So when we deal with carbon, we know that they bond together. So each carbon atom has 4 valence electrons. And then we know we have 4 hydrogen atoms. And generally when you do these structures, they're going to want some kind of symmetry. And so we could put a hydrogen here and here, and then here and here, because they look symmetrical. That line of symmetry goes right here. And then these 2 carbons, those 2 electrons from the carbons, would make that covalent bond. So when you do this, we can see that we've broken a rule. One of the rules that we've broken is we have unbonded electrons, and if we count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, we do have 12 valence electrons. So what we can do in order to satisfy the rule of no unbonded pairs of electrons is these 2 electrons can slide in to the middle here and form what we call a double bond. And it's a double bond because there are 2 pairs of electrons involved in that bond. So when we do that, we have 1, 2, 3, 4, 5, 6, 7, 8, and then the hydrogen comes in with 9, 10, 11, 12. And so if you ever are in the situation where you have those unpaired electrons, they would need to go in and form a double or even sometimes a triple bond. And so carbon is very common to have these multiple bonds. Carbon and nitrogen are it's not uncommon to see them form multiple bonds. So here your double and triple bonds, your double bond shares 2 pairs of electrons, your triple bond shares 3, and like I said, your nitrogen's very common to do that. You can see here that it has 1, 2, 3 unpaired electrons when they bond together, so they would naturally pair up. So nitrogen 1, 2, 3, and I'm going to put the lone pairs on the outside. And so you can see that this one could scoot down to pair with this one when it scoots down. This one will move in, as will this one, and they will form the triple bonds there. And so that's, I think, where we're going to stop for today with 9.1, because there's many that break these rules here, and we'll talk about those starting next week.